Okay, yeah, so thanks everyone for joining this session, either virtually or in person. So this is our interactive theorem proving for maths and research workshop. So if you want to follow along, there's some instructions on the workshop webpage. If you go to xlean.org and then hit the blog, and there's a workshop announcement. So, and it should also be in the chat as well. So this is the workshop page, and I've got the timetable down here. And we've got, so this is the full timetable, and then we've got what we're doing now. So right now we're going to be looking at Lean via the game engine. So I'm gonna go to the game engine, and to do that, you can just click on this link here where it says natural number game. So up in a new window. Yeah, so the natural number game engine is how you'll be navigating the basics of Lean. So if you've got this up and running, we'll start with the tutorial world. I'm going to just click on this little button here. And we'll start. Okay, so what's happening here is that we're being asked to prove this result, that 37 times x plus q is equal to 37 times x plus q. And we can see we've got some objects. These are the variables, x and q. And we also have the goal, which is to prove 37 times x plus q is 37 times x plus q. And we're going to do this by using a tactic called reflexivity. So reflexivity allows you to prove anything of the form x equals x. So if we go over here, I click on this, it's telling you what the tactic is. So reflexivity allows you to prove that. So I'll just type in RFL, and there's something in the chat. Have you seen that? Yeah, so we've completed that level. So we'll go to the next level. And in this level, we've got the objects, these being the integers or the natural numbers x and y. And now we also have an assumption, which is that y is equal to x plus 7. And we want to prove this goal, that 2 times y is equal to 2 times x plus 7. So with Lean, what you can do is you can actually rewrite the goal. So we're going to transform the goal using the assumption, and we'll do that using the rewrite tactic. So if I type rewrite and then an H in brackets, we can hit execute. Okay, so what's happened here after typing the rewrite H? What we've done is we have this expression y is equal to x plus 7, and we've replaced every occurrence of y in the original goal with x plus 7. So the original goal was to prove that 2 times y was equal to 2 times x plus 7, and we've replaced the y there with x plus 7. And what tactic can we use to finish that off? Well, we've got the reflexivity tactic, which proves a thing equals itself. Okay, so that's that. So in this level, we want to prove that 2 is the number after 0. And here we can see that we can use the reflexivity tactic with theorems as well as hypotheses. So there are no hypotheses here, there's just the goal, but we also have these theorems on the side. So we've got all of these theorems. So these theorems say, for example, that 2 is equal to the successor of 1. So what's going on here? What on earth is this suck business? Well, this is how natural numbers are defined in lean. So in lean, a natural number is either 0 or the successor of another natural number. So suck 0 represents what we ordinarily think of as 1. So I'm going to just type in here, rewrite, and we'll replace the 2 with the successor of 1. And we can hit execute. Oh, no, there's something in the way. Okay, so then we can rewrite again. We'll rewrite with 1 equals suck 0. And execute. And now you can see that both sides are the same, so we can finish off with reflexivity. Now this looks like exactly the same problem. So what's different here? Well, we're going to use rewriting in a different way. We saw that what rewriting does, in fact, let's look at exactly what this theorem states. So this theorem that we were using before, 2 equals suck 1, is the proof that 2 is the successor of 1. But we can also use, let's look at this theorem. It says 1 is the successor of 0. So when we in the previous instance use this theorem, 2 is equal to the successor of 1, and we rewrite 2 looks like 1. So when we did that last time, what happened was it replaced the 2 here with the successor of 1. But we can also go in the other direction, and now I'll show you the retry facility of this engine. So if I just click retry, it undoes what we had done. So I'm going to now use a different result. I'm going to use this result here, 1 equals the successor of 0. But if I try that, let's see what happens. I'm going to hit execute, and it's giving me an error message. It says tactic rewrite failed, did not find instance of the pattern in the target expression. Why is that? Well, what it's wanting to do is look for the left-hand side of this equation. So the left-hand side is 1, and it's going to try to replace it with the right-hand side. So what we need to do is to ask the tactic to go in the other direction, and to do that, we use a left arrow. We type the left arrow with \L. So I've typed the \L, and then I hit plus, not plus, space or tab. I'll just do that one more time. \L space, and then I hit execute. Okay, so I've replaced 2 with the successor of 1. I can then do the same thing. We're going to replace 1 with the successor of 2. We're going to replace the successor of 1 with 2 using this result again in the backwards direction. Okay, so now we've got to prove 2 equals 2, which we do by reflexivity. Okay, so that's that. So I'm going to let you go through the rest of the tutorial world yourself. There's not much more to learn on the tutorial world. I'll show you the addition world. So let's go to the home page. So usually you can't skip levels, but we're going to change the rules to relaxed, which allows us to skip levels. So let's move over to the addition world. And I'll just show you again what I did in case you didn't see that. So I moved the rules to relaxed here, which allows you to skip. So we go over here, we'll start. Okay, so we're going to prove now that 0 plus n is equal to n, and we have to know what is meant by addition in order to be able to do that. So addition is defined, if we look over here at the definitions, it tells us how addition is defined. So addition on natural numbers is defined by two definitional equations. One states that anything plus 0 is itself, so a plus 0 is equal to a, and another rule says that a plus the successor of b is equal to the successor of a plus b. So you might think that we can prove that 0 plus n is equal to n just by applying add 0. It looks very similar, but of course we don't have commutativity of addition. So how are we going to prove this? Well, we're going to prove it via induction. So that's the next tactic we want to look at. We look at the induction tactic. And this is describing how it works, but I'll just indicate how we start off. So we start off by typing induction n with DHD. So what's going on here? I guess it's maybe not evident what's happening until we hit execute. So what's happened when I hit that is that we see there are two goals now. There's the active goal and goal 2. So the active goal is to prove that 0 plus 0 is equal to 0. And goal 2 is this. So we have to prove that 0 plus the successor of d is equal to the successor of d. But we also have this assumption that 0 plus d equals d. So what do those two goals correspond to in ordinary mathematics? Well, goal 2 is the inductive case of the induction, and the active goal is the base case. So we're proving this by induction on n. The base case is to prove that it holds when n equals 0. And to prove the base case, we're going to use this definition of addition. So recall we had, well, you could say this theorem, which is, or definitional theorem, which is part of the way in which addition is defined. So we're going to rewrite using this add 0. We hit execute. Now, there's a slight difference between the natural number game and how lean works usually. So usually the rewrite tactic will also apply reflexivity, but this the natural number game has redefined the rewrite tactic so that it doesn't automatically complete things like this. So we have to manually type in reflexivity to prove 0 equals 0. Okay, so now you can see that the base case has been completed and we're on to the inductive step. So we want to prove 0 plus successor of d is a successor of d. And we'll use this rule, add suc. So what it says is that a plus the successor of number is the successor of a plus that number. So if we use this, it's going to replace, hopefully, what it will do, 0 plus the successor of d with the successor of 0 plus d. Let's just see if that's what happens. Yeah, so that's what's happened. And now what do? Well, we can use the inductive hypothesis, HD. So note, we can use rewrite both with hypotheses and with theorems. So you can use it in different ways. Okay. Okay, and now that's something we already know, or it's not, yeah, or we can prove by reflexivity. So okay, that's that. I'm going to let people play around with, well, me, I'll do one more level and we'll let you play around with things and ask questions. Okay, so for this next level, we're going to prove that successor of A plus B is equal to the successor of A plus B. It looks like this add suck definitional equation, but it's not because we don't yet have commutativity. So we can't just say that this follows from add suck. So suck add and add suck are different results. And this is also kind of illustrating part of how theorems are named in Lean's mathematical library. So usually the name of a theorem indicates the order in which the operations appear in the theorem statement. So we've got suck add here because suck appears first, followed by addition. Okay, so now we're going to do an induction, and we've got a choice as to whether to do induction on A or induction on B. Now, since addition is defined inductively on the second variable, it makes more sense to do induction on that second variable. So that's what we'll do. We'll do induction B with, and now, yeah, so now you can see how this works. I'm going to name some inductive variable and an inductive hypothesis. It doesn't really matter what I call it. I'm going to call it K and IH, for example. So we'll hit execute. And now you can see again the two goals. There's the active goal, which is the base case, and then goal 2, which is the inductive case. So let's prove that base case. So immediately we can change the goal by using add 0. So let's go back to the theorems that we have available to us. So all the theorems are down here. Add suck, add 0, etc. So if I use add 0, let's actually look at add 0. Add 0 says that A plus 0 is equal to A. So that should replace this with just itself. So that's replaced the suck A plus 0 with suck A. Now what? We can do the same thing again. So we'll just rewrite with add 0. And now that's something we can prove through reflexivity. Okay, so that's completed the base case, and it's moved us on automatically to the inductive step, the inductive case. So what are we going to do here? Well, what we can do is we can rewrite using the add suck. I'll just show you that again. If I can be looking at this screen. Okay, so we'll rewrite with add suck. So that's going to replace something plus its successor with the successor. So here we're going to replace, well, actually, yeah, there's a question as to what's going to be replaced, because it could work on either of these two expressions, because we've got something plus the successor over here and something plus the successor over here, and it basically reads from left to right. So it's going to work on this bit first. So that's what we will predict will happen. It should replace successor of A plus successor of K with the successor of A plus K. And that's exactly what it's done. Yeah. So it's changed this part of the expression to this. Now we can use the inductive hypothesis if we want, or we could do add suck again if we wanted. Okay, well let's use the inductive hypothesis. Not yet, the inductive hypothesis, which I called IH. Okay, so we still have some work to do because the left-hand side and right-hand side don't look the same. So we're going to use add suck once more. Okay, so now these things look exactly the same. I can use reflexivity. So that's that. So I'll just go see if there are any questions.
So let's say 10 minutes to have a little bit of a play through some of the levels yourself. And then we'd just be interested to have a discussion for a few minutes about how you find this way of introducing lean and the tactics, and just how lean works. Okay, let's just all come back together, including those online. Hopefully you can hear me. You've had a little play now with the natural number game and a few of the levels on that. This workshop is very much an introduction to lean, particularly for those who've never seen it before. So I just wonder if anyone would like to share, if you're in that position of not really having played with it before, what was your experience of using this game engine, interacting with lean in this sort of gamified way? Has that worked for you to introduce some of the tactics? And we will show you later how to use it much more like a programming language. So anyone in the room want to, or online, either drop something in the chat, raise your hand, just unmute. Yeah.
So I've never seen lean before. Since you were talking about it, I think I've seen Coq like 10 years ago, but I don't remember anything about it. Maybe it's because this is like sort of low level proofs, but it felt a bit clunky somehow.
Okay.
Like it's like then like also I have like a problem where like it wasn't letting me do induction because of something inside the system. Like, but that's completely unrelated. But in like a way, like but I get what it's doing, I guess. But if I was like looking at it like on like purely I'm looking at this level like okay, but why am I doing is to like trying to like prove that a plus 1 is equal to 1 plus b in like such like a long and extended way. Like I can see the point, but I can also see the counterpoint sort of.
Sure. So there was still some sort of clunky syntax and internal issues that you were perhaps struggling with a bit, but also there's the sort of philosophical mathematical approach of why do we have to prove this in this particular order.
Like I'm putting myself in like sort of the body of like undergrad myself. And it's like, okay, I can see this working, but if I'm like trying to do something a bit more highbrow, this feels like this will never go anywhere if I have to like take like 6 lines to prove like the associative property of addition.
Sure. Yeah. So to what extent can something that is taking so long to prove some of these basic things be useful for bigger things? We'll come to that, and Kevin particularly, I think, will be talking about lean in research and where we are with those sorts of things. And certainly throughout the history of theorem provers, one of the adages has been the value of it is also very tightly linked to the quality of the library of mathematical statements you have available to you to then be able to reuse over and over again. And we'll come to that and MathLib and how that works.
I think also, I mean, there's the point, what that number game essentially simulated is what you're doing in your first 6 weeks of your first year math course, where you learn how to prove and where you learn what natural numbers are. I mean, there it also takes you quite a while to prove associativity of addition and understand how induction works, even if you do it only on paper, so to speak. And I mean, yeah, if you then have the additions, I mean, I'm for sure lean can do that as well. But I mean, in Isabel, that stuff is proven. But one reason it proves everything automatically is there's tons of libraries from basic math over to very advanced topics, number theory and everything available to the system. It can reuse all those proofs.
So if you're familiar with those things, lean does have those same sorts of things and will automatically do lots of stuff because it has proofs of these things. I've got an interesting comment, thank you, from Nino online. As someone who learns Coq in France before, I find this interactive tutorial approach to familiarize ourselves with the tactics easier to navigate. Okay, so again, maybe that's the experience of people who perhaps come from other systems.
It's also, I mean, for teaching, it's fantastic because it's zero install.
Sure.
Yeah, sorry, I kind of went straight into the game engine without explaining what we were doing, so I should have said. The point of doing these exercises is not to do mathematics, but rather to introduce ourselves to some of the ways in which one writes proofs in Lean. Not that these are particularly interesting results, and not that they aren't in the mathematical library, but we're starting with easy things that can be proved using simple tactics. And later on, we will look at some more interesting mathematics. Yeah.
Any other comments, either online or in the room, Alvaro?
I will bring a bit of a, let's say, different view in this. I think it's a beautiful tool for anyone trying to learn. I would have appreciated this so much, like this new version, when I was doing my undergrad. It just brings a very slow pace but detailed process on how every command works, why you're doing everything, little hints on the side as well, and literally showing you the environment where you're working through Lean. And I think as a student, if you're trying to learn Lean, this is a magnificent tool. It will have the minor details, people complain about, oh yeah, I don't like this, I don't like that, in terms of structure, or maybe the ethics, or maybe how you write commands. But overall, I think it's a very good tool. Yeah.
And of course, one of the things we will come to in some of the talks later is also not just in terms of learning Lean. Learning Lean is great, but learning mathematics, it's interesting to think about how useful is a tool for learning mathematics as well. And if one were teaching about the construction and the foundations of natural numbers and natural number arithmetic, then again, there's a question as to, is this a useful approach? Now,
I haven't played with it properly, but I wondered if when it gives you that like proof, does it come with comments as to why it's doing this in each step?
To an extent. So when it's introducing the tactics and what you're trying to prove in each case, on the left-hand side in the game, there's all sorts of little hints and comments that are programmed in to be able to explain what's going on.
And also you can see what's actually happening by looking at the proof state in each step.
So the objects, the assumptions, the goal. It's telling you what's going on and where you are within the proof.
So here it says that A and K are two natural numbers, right?
Yeah.
Yeah.
IH is one single thing, right?
It's an assumption called IH.
The inductive hypothesis.
Which is IH because Guillaume's called it because it's the inductive hypothesis. And then this is a statement that we can then use. In fact, a little bit above, we use it to rewrite a statement. It's not on the screen. You can probably find it.
So it hasn't done the goal yet. It hasn't proved it. Right?
Yeah, we finished the proof. That was one that Johan finished. So we got it down to the point by rewriting where the left-hand side is exactly equal to the right-hand side, and then that's true by reflexivity of equality. So that's the RFL reflexivity factor.
If you show the students proof terms constructed by tactics, does it help in their understanding? Don't know. I don't think yeah, let's see. Did I use? I think when I've been teaching, I've taken more of a proof term based approach. I guess we can ask the students whether.
Do you want to unpack that for those not familiar with that, those statements? What exactly do you mean by that?
Yeah, what exactly is a proof term constructed by tactics? An intermediate goal or?
Well, let's see. Let's see. So I guess once we've, I don't know whether we can do this in the game engine. So what maybe the question was, actually, I'm not sure what the, well, I suppose when you've written your proof, if we go back to, am I still sharing the thing? Yeah, I guess I am. Sharing the thing. So if I go back to this thing, yeah. So we can actually see, if we click on this little button here, we can actually see the more standard view of the proof. So this is what the proof looks like. Rather than line by line, we can see the whole proof. Now, if we were doing this in not in this game engine, we would be able to then actually see the proof term that this theorem represents. So what is that? So that's, I guess that's.
So after each application of a tactic, you mean, or?
Oh, I don't know if that makes sense. I don't know. What would that mean?
Well, to partly answer the question, one of the things that we are exploring, and we've got some student interns who will talk to us a bit later, is how useful is it, for example, to be able to take the lean and to translate that line by line, tactic by tactic into this is what the natural language version of that is. So that students can see that read across from the lean, each line of the lean proof, the tactics you're using, to what does this mean in terms of the natural language statement and what you've done.
Oh, okay, well, yeah, so that's one thing. I think what was being referred to here is what the tactics are doing, they're I guess they're in the meta language of lean, and they produce terms in the in lean itself. So what this is it's I guess it's a program that produces a proof term, and the question is that more helpful for the students to see or not?
I'm still wondering what proof term means in that context. The intermediate goal, the intermediate steps that I
I
get,
don't think, yeah, okay, well.
or the certified proof that, for example,
Oh,
code
the term you put
generates.
in the refined tactic, okay, yeah. So, yeah, okay, yeah, so I guess you could do that.
I mean, what I can clearly confirm, and I will tell later,
Yeah.
our experience with Isabel is that having students that have hardly any background in proving, by starting with a more computer science approach, they learn rather quickly how to prove using Isabel, and I'm pretty sure that would be the same in Lean. The user interfaces of the systems are copying the good things from each other. So there's clearly a point in there that students can learn with those systems a lot of things that they might not learn as quickly from a textbook.
Yeah, but there's certainly, I think there's certainly a lot of debate regarding whether the proof term-based approach is better or worse than the tactic-based approach. I don't think anyone's got a clear answer to that yet. So the next thing I wanted to do is so you can keep working on that, but for those of you who haven't used the mathematics in Lean thing yet, I'll show you how to start doing that, and then we'll continue in the afternoon. So if we go back to the, oh, yeah, sure, I should look over here. We go back to the workshop web page.
Next tab.
And we can go to the timetable, which is over here. Oh, it didn't actually format my LaTeX correctly. Never mind. So we're going to go to, we're going to be looking at mathematics in Lean. So this is an online textbook. So if we click on here, let's see if that opens up in a new tab. Yeah. So we've got the textbook here, which we'll be looking at, but it's associated with a repository as well. So if we go back over here, I guess we need to use the back button. It's associated with a repository. So I'm assuming you've all set up a GitHub account. So I'll click on this. That should take me to the repository. So what you need to do is you need to click on code. So we're going to be using this in the browser using GitHub codespaces. So if you click on the code button, what you should do if you don't already have a code space here, you can just, so let's click on plus, and that will create a new code space, and that's going to take a few minutes, and that's kind of why I wanted you to do it now, because it takes about 5 or 6 minutes to create a code space, and then we'll return to that in the afternoon. I just wanted you to get set up. Okay, so we've got some more questions. It actually does when there are no rules. That will show the proof term. Okay, I'm not familiar with this tactic. So show term, let's try this. Do we just, how do we, where does that go? Does it go around the?
Okay, can you hear me?
Yes.
Okay. Yeah, you can put it anywhere you want, but it doesn't always give you the best results. But you can put it around the whole proof, and then it will show the show the full proof term.
So is that, no, that's not doing it. Okay, well, okay, thanks very much. I guess I didn't know about that one.
I'll put something in the chat that should just work if you're in relaxed mode in the game engine.
Oh, you have to be in relaxed. Oh, of course, yeah, because it doesn't know. It doesn't know the tactic.
Or none, something.
The none mode, yeah.
Now, if you click on the show term, it will show you the term. Of course, it's trivial here, but I just.
Yeah. What is it?
It's actually doing it, but because in the exec there's already the exact term, the proof term is already there, so it's
Okay.
showing the same.
Yeah.
Okay. Okay. Yeah, and for those who are just setting up the code space, do you want to just run over it once more, just in case?
Yeah, I'll just do that one more time. It's still creating it. So where? There's something, yeah, something in the way. Yeah. Right, so yeah, so if you were wanting to set up, I'll show you again how to set up the code space. So we were on the blog, we went to we were here, it says mathematics in lean, so we just click on mathematics in lean GitHub repository, or you could do a search for it. So here we are in GitHub, and we're going to set up basically a virtual computer, roughly speaking. So you click on code, and if you didn't already have any code spaces, it would ask you to create a code space on master, I think, and we already have a few code spaces. And I would just click plus or create code space on master. And it takes a little while to make that. It looks like it's created it over here.
So you're not expecting them to do anything with that now, but
Yes.
we'll come back to it later.
Yeah, we'll come back to this later.
Okay.
But for the moment, if you want to continue working through the natural number game.
Okay, so thanks very much, Johan. And what we're going to do now is just have a little break and opportunity for those in the room to grab a coffee and a little snack. We start again formally at 11 o'clock. We'll stay in the Zoom meeting. If anyone does want to drop any questions in the chat, either through the Q&A tab or in the chat itself, by all means do so. Likewise, those in the room, don't be afraid to ask. It's an opportunity if you want to continue to play with the natural number game and do some more levels or whatever is useful. So we'll mute in the room, and as I say, we'll all come back together at 11 o'clock in order to start our series of talks. And yeah, we'll see you in a little bit.